Good morning, everyone. Thank you for letting me participate in this conference. My name is Javier Mascarós. I work as a R&I technician in Global Omnium, Valencia, Spain. I am going to present to you the project I've been involved in the last 2 years. The project is called PORTABLECRAC, a novel portable technology for the regeneration of granular activated carbon. This photograph shows the microscopic detail of an activated carbon granule. It contains a complex net of pores which creates a large surface area. This characteristic grants the activated carbon with its main attribute, a high adsorption capacity. Having said that, I will give you a short introduction about the carbon market and its management. I will also explain the main points of the project and the current situation. The image shows a GAC open filter having a backwash in our facilities. The pie chart shows the industries where the activated carbon is normally used. The water treatment and the air purification industries are the top ones. The demand of activated carbon has increased from 2.7 million tons in 2015 to 5.4 million tons in 2021. It is worth mentioning that most of the activated carbon is manufactured overseas, mainly in China, and Europe imports about 80% of its internal production. In our company, Global Omnium and Emibasa, around 3,000 cubic meters of GAC is used for water treatment in both open and pressurized filters. During the use of activated carbon to retain contaminants, the porosity becomes progressively saturated and inactive. In small facilities, when the carbon reaches its saturation limit, it is usually taken either to a landfill or to an incinerator. However, in facilities where a larger volume of carbon is used, the preferred option is to regenerate it through a thermal process. These practices are known to require off-site service, high energy input, and carbon losses with significant environmental and economic impacts. Thus, PORTABLECRAC proposes an alternative: the use of electrochemistry technology to regenerate saturated granular activated carbon in situ. As the image shows, during the regeneration process, an electrical potential difference is applied between two electrodes in a compartment filled with saturated GAC and electrolyte. As a result, the equilibrium between the absorbed substances and the carbon pores is modified, causing the detachment of these substances and therefore the recovery of the original carbon properties. Some advantages of this process are captured in the slide. The project we are working on is called PORTABLECRAC, Portable Solution for the Electrochemical Regeneration of Activated Carbon. It is funded by the European Commission and belongs to the Horizon 2020 Research and Innovation Programme. It has a total budget of 2.8 million euros and a duration of 36 months, extended 4 months due to the epidemic. The consortium is composed by 5 companies and 2 universities. In terms of the work streams of the project, there is a package dedicated to the design, adaptation and construction of prototypes. Then it follows the development of the regeneration demos along with a technical and economical validation. And finally, there is an investigation carried out to determine the most suitable treatment to enable the reuse of the liquid waste generated in the process. Regarding the design and construction of the prototypes, I present to you the 3 versions we have already built and operated. They have different configurations and will adapt to different customers' needs. Images show the batch prototype. As its name suggests, it works in a discontinuous mode, The image on the left represents the batch prototype at laboratory scale, designed and operated by the University of Alicante. It has a treatment capacity of 15 kilograms of carbon per batch. On the other hand, the batch prototype on the right-hand side is a bigger version which has a treatment capacity of 100 kilograms of carbon per batch. The continuous electrolyte carbon bed prototype consists of a cylindrical vertical reactor with the option of operating in continuous mode thanks to an automatic loading and unloading system. Like the batch prototype, a smaller version was initially constructed and operated. It has a treatment capacity of 10 kilograms of carbon per batch. Then a bigger version was constructed with a treatment capacity of 210 kilograms of carbon per batch. As it can work in semi-continuous mode, it is able to regenerate more than 500 kilograms of carbon a day. The continuous carbon electro-regeneration prototype has been designed and constructed based on the principles of the electrical sludge dewatering technology using a belt press. It is placed in a container and can operate in continuous mode. It can treat up to 0.6 kilograms per minute, which is a total of 280 kilograms of carbon in a standard 8-hour shift. We have arrived to the point where I will explain the current situation and show a few results. Some parameters can be tuned in order to optimize the regeneration process. These parameters are distance between electrodes, volume, flow and concentration of electrolyte, residence and treatment time, and current density and electrical voltage. Then, the way we assess the performance of the regeneration is by the study of different indicators such as microvolume recovery, surface area recovery, electrical consumption, chemical consumption, and adsorption assessment of the regenerated carbon. The following graph shows the nitrogen adsorption isotherms obtained at 77 Kelvin from a favorable test carried out with the batch prototype. It represents the volume of gas adsorbed in the carbon sample at different pressures. It gives an accurate information of the adsorption capacity the carbon has. As it is observed, the adsorption capacity is well recovered after 1 hour of treatment, purple line. The area of the carbon increased from 660 square meters per gram to 805 square meters per gram. The surface area of the pristine carbon was 890 square meters per gram. This chart shows the recovered volume at different pore sizes during the regeneration. The sample taken after 2 hours of treatment shows a significant volume of pores below 1 nanometers closer to the pristine sample. However, the sample taken after 1 hour of treatment is still the one with an overall highest volume of pores. Regarding the regeneration performance assessed from the tests carried out with both the batch and the small cc prototypes, the results were favorable. 4 tests of the 7 carried out with the batch have shown that the adsorption capacity can be recovered above the 80% mark in 1 hour, which is the threshold set by the project. Likewise, the results obtained with small cc show that it is capable to achieve a recovery of the adsorption capacity above the 90% mark in just 21 minutes. The liquid waste generated electrolyte plus contaminants was characterized in order to study the most suitable treatment for either discharging it to the sewer or reuse it. This work is being carried out by the University of Vigo. Looking at the table, it can be seen that overall the organic and inorganic concentrations are rather low. For the removal of inorganic substances, the preferred treatment would be a neutralization and precipitation. The final effluent generated after a neutralization with sodium hydroxide or calcium carbonate can be directly discharged into the environment, and the sludge generated can be disposed in a landfill. Besides, a combined use of persulfate and electrophotochemical treatment has been proved to be a fast and effective technology for the COD removal. Finally, I would like to mention that PORTABLECRAC project follows the strategy of a circular economy. It suggests a flexible solution which allows in situ regeneration of activated carbon using a compact and portable device capable to adapt to the client's needs. It is expected to significantly reduce the CO2 emissions, to achieve a zero waste discharge model, and to lead to the creation of a new production line resulting in new jobs. That is what circular economy is all about. It is about simulating the economy of the environment by closing the loop, minimize waste, and make the most of the resources. This is the bibliography employed. Finally, you can follow the path and visit the project's website in case you are more interested in it. And that is all. Thanks very much indeed.